we have presentation from Phuti Ngoepe. He is a professor at the University of Limpopo in South Africa, and he will give a talk about nanostructured metal oxide electrodes for energy storage. Phuti?
Well, thank you very much for the opportunity to make a presentation. I'll be talking about the generation of nano-architectured materials, metal oxides for battery materials. My talk will be outlined as follows. I'll have an introduction and share some results on the validation of results, synthesis of binary and ternary compounds, and performance of nanostructures. This is an acknowledgement of people that I've worked with and then the funding bodies that supported us. Now, this shows the South African Energy Storage Consortium with different participants, starting with the precursors going over to materials characterization, cell and pack engineering, and life testing, diagnostics, battery cycling, etc. So there are different institutions in South Africa that are working around this. Now, our center works on minerals, metal alloys, and energy storage materials, and we mainly work on the manganese-rich energy storage materials, and we also study beyond lithium and batteries involving lithium air and lithium sulfides, and some anodes such as titanium dioxide and silicon. The various techniques that we use are along the length scales, starting with the ab initio density functional, semi-empirical methods, classical methods. These involve mainly atomistic simulations and force field, and enable us to determine microstructures in materials which can give us valuable information. Now, this gives roughly an idea of where the density functional methods work and where the empirical methods work, like linear scaling methods that enable us to find particles that are found in cathode materials, and these increase in size from to various nanometers, where we have 20,000 atoms, and then 100,000 atoms up to 1 million atoms. Now, those primary particles can be put together to form secondary particles, and these will sort of simulate what we actually find inside the reactor, where we have secondary particles consisting of a number of primary particles. Now, I'm just giving here an indication of some work that we did a long time ago, which is now re-imaging on fluorine ion conductors, which shows a very good correlation between experimental results like laser spectroscopy, Brilliant spectroscopy, Raman spectroscopy, and how those related to the molecular dynamic simulations that can be carried, and which show different types of defects, particularly in calcium fluorides that are doped with lanthanide fluoride, and those that are doped with terbium fluoride. The manner in which these elastic constants change show us where there is an onset of the first ion phase in the material, and we can see the differences in the manner in which these materials change. And this is another example where we did the prediction of the defect models in first ion phase. These were determined from the relative changes of elastic constants obtained experimentally, and those obtained from defect models, Frankel defect model, Schottky defect model, and we are able to say that those changes that occur here at high temperature are more associated with the Frankel model from the simulations. I'm now going to just share work on the simulated synthesis of electrodes. And you know that the microstructures give a lot of information about materials, but how microstructures can be simulated can be very, very challenging. And also the different types of nano architectures, you know, can give us fast charge or long life battery, but how they are simulated is also a challenge. And in some instances, we found composite electrodes consisting of uh, polymorphs of the same compound manganese dioxide, for example, having what we call the Ramstellite structure and the pyrolusite structure. How one can simulate this in a spontaneous way is quite a challenge. Now, I'm going to show you two examples of manganese dioxide and titanium dioxide, which are simulated by a technique which we called amorphization recrystallization method, which is a technique that is able to amorphize the material and leave it to evolve. And as it evolves, we can see a stage where the configuration energy stays constant, which is a process of nucleation, and where it drops, which is associated with crystal growth, and where it levels again, associated with the fully crystallized materials. Now, these techniques are able to give us, for example, in this case, a nanoporous structure of Li MnO2. And here we have a simulated structure which has some channels. And these channels can be seen here. They are nicely symmetrically distributed, but they are equivalent in shape to what we found with high-resolution transmission electron microscope. And here we see the tunnel which the lithium can be able to move inside the cathode. Now, in this one, we have a nanoporous structure of titanium dioxide with its microstructures. And we see here again the channel through which the electrolyte can move. We see the tunnels here marked in red. And these tunnels are seen to be having zigzag patterns corresponding to the Brookite phase and the straight patterns corresponding to the Routel phase. And here we have simulated the entrances through which the lithium, which is in yellow, can move into the material. But on the right-hand side here, we have a pattern of entrances which is found by simulations, which is very, very close in pattern to the high-resolution transmission electron microscope. So in this way, we are able to model these complex microstructures. Now we are going to look at some of the compounds that are used currently in very, very powerful cathode materials like the layered Li2MnO3. These, are found from the combination of Li2O and Mn2O. And what is known is that the Li2MnO3 is not electrochemically active. However, the nano Li2MnO3 is electrochemically active. Question is, what is the origin of that electrochemical activity? And we found that in the structure of the Li2MnO3, we have what we call the oxygen layer, and a layer which is consisting of manganese and lithium. Lithium is in yellow, and some layers which are consisting of only lithium. Now, when you charge the material, you take out the lithium out of the system, and when you have these layers which consist of lithium only, the system ultimately collapses. And when you discharge, they can open up. And when they can open up, then the system becomes electrochemically inactive. However, if you make them nano, then you introduce some of the manganese in these layers of manganese, and ultimately the manganese in that layer acts as a pillar, so that as you charge, you remove the lithium, then the manganese remain a scaffold that makes the layers open. And then this is open for discharge and charge, and in that process, then we are able to use this as an electrode. So that is the origin of the electrochemical activity. Another important material is the spinel LiMn2O4, which is less costly and quite powerful. And this has also been grown by amorphization, recrystallization. You have nucleation and crystallization of the materials. And this represents just a primary particle in a secondary particle consisting of many primary particles. And when you cut it in the middle, you get a microstructure, which is composite. It has a layered structure and spinel structures in it. Now, the interesting part comes when you try to charge and discharge this material. It moves from what we call a cubic spinel phase to a tetragonal spinel phase. But between these two phases, you have a multi-grained phase at the concentration of 1,75. And this is a disruptive phase, which does not make it easy for you to charge from the cubic to the tetragonal region. And we can see from this picture here that this multi-grained phase corresponds to X-ray patterns that are very broad, whereas the other two extreme regions consist of patterns that are very narrow, which means that they are highly crystalline. But we also see that this phase here, which is the spinel phase, corresponds to voltage, which is around 3 volts. And that voltage drops when you go to 1,75 to this phase. And then when you go over to the tetragonal phase, it remains low. Now, the big question is, how can we limit the generation of the multigrains in this intermediate phase? But the main purpose of this study was just to be able to identify this phase, which is 1.75, which we have found in our study. Now, I'm going to just study another way in which we look at the performance of these materials, how we predict the performance. In this case, we have we can apply uniaxial pressure to what we call the porous structure and the bulk structure. And when you apply the same strain to the porous and the bulk structure, then the bulk structure experiences a very high pressure. And when you look at the X-ray patterns, we realize that the X-ray patterns split as you apply the pressure or when you put lithium inside that structure. In the case of the nanoporous structure, we realize that these peaks don't split, they just shift towards the left, which means that there isn't much structural change in the porous structure. And this picture here just shows how the pores, which are these, the pores through which lithium, which is in yellow, can move through. It is represented by this number C, and that number C corresponds to this peak C. And you can see that as you apply pressure, when you put lithium into this bulk structure, that peak shifts significantly. When you do the nanoporous structure, that peak doesn't shift. Now, this means that the nanoporous structure is therefore very good and ideal for taking lithium in and out, and we can charge and discharge the system without the structure being destroyed. And lastly, in this work, the important thing is that we are able to predict these microstructures, but we use materials modeling to do this. And this gives us a way in which we can look at battery modeling, and the battery modeling translates into vehicle modeling. And in vehicle modeling, you can look at the performance of the vehicle and the range that the vehicle can travel without being discharged, from the microstructure that we have generated. I'm going to skip this portion and go over to the conclusion. So we have looked at the way in which and indicated that these simulations can well be validated by experimental results. We have seen how we can generate complex structures, microstructures together with the nanostructures using these special methods. And we can also look at mechanical properties which show you how the systems behave during charging and discharging. The big challenge is to sort of see how we can enhance the spinel performance by going through that transition, which I call 1.75, in order to get more performance out of the spinel structures. Thank you very much.